So yesterday we proved that the estimation error epsilon has zero mean. Therefore, the linear MMSE is an unbiased estimate. Now let's quickly find the estimation error covariance. Since it has zero mean, the estimation error covariance will be given as epsilon epsilon transpose, expectation of that, and this is estimation error covariance. So what is epsilon? Epsilon is so this one is the estimation error. This one, right? X minus x hat. So this we can write as x minus. So the initial guess of x is x tilde. Let's subtract and add x tilde. This x minus x tilde is nothing but x dash. So this is x dash, and then this is the estimate of x dash. Right? So instead of writing x minus x hat, you can also write x dash minus x dash hat. So let's do that. We are interested in finding the covariance of this. In separating terms, we have so we have four terms, right? So what can we say about the four terms? So you know some of them. So expectation of x dash transpose is equal to p. We need to know this thing, right? Initial error covariance, right? So we can replace the first term, expectation of x dash hat, as p. The first term will be p. This is p. Now we need to find the second term. The third term will be just transpose of this second term and the fourth term, right? Now to find the second term, we need to substitute for x dash hat. We know x dash hat is equal to C y dash, and y dash is equal to h x dash plus n. We did this many times yesterday, so let's substitute this one here. So C and H will go out. And we have x dash transpose, and we know that n and x dash are independent, right? n and x are independent. Therefore, n and x dash will also be independent. And expectation of x dash transpose is p. So from this we get p. And what is the expression of C that we got last time? It is pH transpose W inverse. So we'll now substitute this law. Let's find the other terms also. Let's substitute pH transpose HP H transpose plus W inverse P HP, right? But if you notice carefully, this is symmetric because HPH transpose is symmetric, P is symmetric, any error covariance is always a symmetric matrix, W is also symmetric. Therefore, the third term, which is the transpose of this, is the same because it is the transpose of the second term, and we know that the second term is symmetric. From the expression we can clearly see that the second term is symmetric. Therefore, we just need to write the same thing. So second and third terms will have the same expression. How about the fourth term? Let's find the fourth term. It is expectation of x dash transpose hat. We need to substitute y dash. Here we know x dash is C times y dash, and C is deterministic. What is this one? Yesterday we derived the expression of this one, I guess. Let's see if we derive this. No. Yes. So HPH transpose plus W. We derived this yesterday. And then C transpose. Now we are going to substitute for C. We know C is PH transpose, and then this inverse. This inverse is here. If you look at the expression of P, we have the whole thing inverse. So we can eliminate that and then write the expression of C transpose. C transpose is HPH transpose plus W inverse. Then H, P will come because we are transposing this one, C transpose, right? So this term will come on the left. Then we have P and then H. Then we have H and then P. And then the W term is also there. There's one more term. Here we have this W. Okay, W is there. Yeah. Now just see the second and third terms have negative sign before, whereas the fourth term is positive, right? Now carefully, if we see these terms, this is the first term, this is the first term. This is the first term. No, this is second. This one is first. This one is first. This is P. This is first term. This is second. This one is third. So let's write all the terms together. The first term is P, then the second term is this one only. So 2 times we have this term. You just see the same expression we have. And then again the same term, but it is plus. PH transpose H P H transpose plus W. So we have P minus PH transpose if you take P outside, we have identity matrix, and this one is C. So CH and then P. So this is the error covariance matrix. Okay. Now, since we are dealing with vectors, X, the unknown quantity is a vector, we have error covariance matrix, but we can also find error variance from this. How? If you expand this one, you will, so each epsilon term here has a number of elements, correct? So epsilon we can write as a vector, right? Epsilon 1, epsilon 2, like that we have this many terms, right? And then when we are doing transpose, we have basically a row vector, epsilon 1 dot 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 up to we have epsilon n. Here we are just multiplying epsilon with epsilon transpose within the argument here. So we basically get a matrix after multiplication, right? Now the estimation error variance is actually the trace. Let's call this matrix sigma, capital sigma. Okay. So estimation error variance is actually the sum of the diagonal terms. Now we have not written the mean separately because in this particular case mean is 0. And this is nothing but the trace of the matrix sigma. So we can find the estimation error variance even for vector x. In that case, we just need to find the trace of the error covariance matrix sigma. Okay? Any question? Do you have any question?
No, ma'am.
Murali, are you there?
Yes, ma'am.
Are you following?
Yeah.
Krishna?
Yes, ma'am. Following.
Okay, now see, to derive the batch estimator, we considered a batch of measurements, right? As we have many measurements, the size increases, right? Here we stacked capital N measurements, right? So, although this estimator retains a desirable property of MMSE, it actually incorporates both prior information and measurements. How we can say that? We just look at the estimation error covariance. In the case of the WLS estimator, we just had a term in the error covariance which was dependent on W. But here we have terms. In this expression, you can easily see that we have P term. P is actually the initial error covariance. We also have W. So this estimator actually, so linear MMSE considers both prior information and measurements. To find the estimate. And it is linear. So it has all the desirable properties. It considers both prior information and measurements, and it is also the estimate is also a linear function of y. So there is no chance of increasing the measurement error and distorting the PDF. But there is a downside. What is that? We are considering a batch of measurements. We need to consider all the measurements together, right? So the computational load is more. It is computationally expensive. Now, whenever we are estimating something, in most of the cases, we want the estimate in real time. It's not that there are some applications, for example, surveying, mapping, where we are interested in increasing the accuracy and getting offline estimate. But generally in navigation, we are interested in doing something in real time. As and when you get measurements, you process with an estimator and find the estimate. Although the batch estimator has all required properties, it is computationally expensive. Therefore, we cannot expect it to provide an estimate in real time. We are stacking a number of measurements. If you think of each measurement, each y vector obtained at a particular time instance, we are actually stacking all the measurements of different time instance, and then only we are applying the batch estimator and getting the estimate. So some of the estimates are definitely not in real time, and also as the batch size grows, the computational load increases. So we want to retain all the properties, at the same time we want to reduce the computational load. How can we do that? We reduce the computational load by having recursive implementation of the batch estimator. Which is the current filter. So Kalman filter is the recursive implementation of the batch estimator or linear MMSE estimator. So it has all the required properties. It gives weight to both prior information and measurements, and it is also computationally simple because it implements the batch estimator in a recursive manner, meaning as and when you get get a measurement, you process and give the estimate. Then at say first instant you get measurement, process, give estimate. Second instant, based on the previous estimate, use the measurements and then give refine the estimate. So this way recursively it actually implements the batch estimate. You already did some sort of recursive estimation for that simple problem. I mean, those who did would have seen that you are actually doing it iteratively. So that's some sort of a recursive implementation, and the Kalman filter actually does that. It takes one measurement vector at a time, processes it, gives the estimate. The next time when another measurement vector comes, it processes and gives an estimate. In this class, we are not going to derive the Kalman filter equations, but I am going to send you a material over email where you will find a way to derive the Kalman filter equations. Okay, there are many ways we can derive the Kalman filter equations. One of the approaches is to actually take these batch equations and show that the Kalm filter is a recursive implementation of that. But that is a little involved, so I will send you the material which actually derives the equation in the easiest way. Okay, it is straightforward. If you go through all the lectures till now, you will be able to understand it. There is nothing great about it. I mean, nothing difficult about it. Of course, it is quite impressive because we are having all the desirable properties and at the same time a recursive implementation. But the derivation is that I will send you is easy to follow. Uh, Here we'll discuss the equations and if possible some properties. So what is our objective? Our objective is here we are interested in a recursive implementation. So given, we assume that the estimate is given at some time instant k. So given xk hat, k is the time instant, and we call it plus xk hat plus. You will understand why I am putting this plus, which is the conditional estimate of x. X is a vector. Okay, conditional estimate of x at time instant k given all the measurements. Okay, so y1, y2. So these are all different measurements. The subscript denotes the time instant. We have considered measurement up to k instant, and then we have found the conditional estimate of x. So given this estimate and the error covariance sigma k, so you will understand why I am writing it this way. Not this one for simplicity. Okay, this one. This is the estimation error covariance. Earlier we didn't have plus in the superscript. You will understand why I am putting this plus. This is the estimation error. This is actually epsilon. This is also an unbiased estimate. Now this we have found based on all these measurements. So given these two terms xk hat and sigma at time instant k, we want to find them at time instant k plus 1. This is why we call this a recursive implementation. Okay, this is our objective. Okay. Now, in order to have a recursive implementation, we are going to use the state space model. The state space model has both the state transition equation and measurement equation. So, this is how we model the system. Let's assume linear because the original Kalm filter equations are for linear system. So we assume a linear state space model. Okay, so this is the state transition. We are actually transiting from kth instant to k plus 1 instant. Okay, so this is the state transition model, and this is the measurement model, right? H is the measurement model matrix, H, and A is the state transition matrix. This is a deterministic input, and we multiply this G matrix. So in K is is a deterministic input. Often in navigation problems we do not have any U, okay, any deterministic input. So we are going to we will considering it's a deterministic input vector. Now V is the measurement noise. We assume it is Gaussian distributed, okay, with zero mean, and covariance. Let's say since we have used W for the state space model, or state transition model, we will not write W here, so let's call this R. Okay, R can change with time. Okay, it's not necessary that R has to be constant. R can change with time. Okay. Now we assume that it is a white noise. The bandwidth of V is more than the bandwidth of interest, the bandwidth of X. Okay, so V is assumed to be white noise. Now we understand why we have V in the measurement model, because when we are making measurements, we cannot guarantee that there is no error. In fact, there will always be an error. So V actually models that measurement error. But how about W? Why do you have this WK in the state transition model? So see, the state transition model actually represents the dynamics. So this represents dynamics. How X is changing? What we mean by dynamics here? How X changes with time. Okay. Now we are actually feeding a model to the filter. So we model the real world behavior and then feed it to the filter. But what is the guarantee that the model actually represents the real world behavior? In most of the cases, it does not happen because we make some approximations. We cannot completely model the real world behavior. Okay, so we make some approximations, simplify the behavior, and then model it. So generally, the state transition model approximates the real world behavior, and we feed that to the filter. We tell the filter that this is how the real X vector changes with time, but we make some approximations in that. Now, how will the filter know that the model that we are feeding to it is an approximate one? That information is actually provided to the filter using this WK vector. So this is called a process noise. We are actually telling the filter through WK, we are telling the filter that the state transition model is not accurate. It has some approximation. If W is 0, then the filter would think that the state transition model is accurate, and it will give a lot of importance to the state transition model. In fact, after some time, it will ignore the measurements. It will not learn anything from the measurements. It will completely rely on the state transition matrix, state transition model. And since the state transition model is not accurate, it will eventually deviate from the actual state vector. And we do not want that to happen. So for the Kalman filter to behave properly, we always inject some process noise. And this is called noise injection, process noise. And this process noise tells the filter that the state transition model is not accurate. For example, suppose we are designing a Kalman filter for a navigation problem where the vehicle has position, it's a moving vehicle, so its position changes and it has some velocity and acceleration as well. Okay, but in the Kalman filter model, we do not consider the acceleration state. We just want to estimate position and velocity. So xk in this state transition model, xk contains position and velocity states, and we use these position and velocity states to transition to the next time instant. We do not consider the acceleration, but actually the vehicle sometimes accelerates, right? So that inaccuracy is accounted for in this W term. Okay. So W actually tells the filter that you should not believe the state transition model completely. It has inaccuracy. If W is large, then filter would know that a state transition model is not so accurate. If W is small, then filter would give more importance to the state transition model. So by suitably choosing W, we can actually change the filter behavior. So this is called tuning. Okay. That's a different topic altogether. We will not get into that. But for the filter to work properly, we need to give all these parameters correctly to the filter. For example, the measurement error information, the covariance, and then the process noise. These terms should be properly determined and fed to the filter. Otherwise, the filter will not work properly. Okay. Now, how do we model W? Again, we assume that this is Gaussian distributed. Generally, we consider zero mean and covariance, which can also change with time. Q. Okay. And W also generally assumed to be white noise. Okay. Then we also assume that the process noise, process noise and measurement noise are completely independent. They are actually from different processes. So measurement error gets added when we make measurements. Process noise accounts for any inaccuracy in the state transition model. So they are actually completely different things. And it is reasonable to assume that they are independent. In this case, this implies they are independent because W and V are Gaussian. Okay. We can also call that they are uncorrelated. They are uncorrelated. In this particular case, all of these are equivalent, uncorrelated independent because they are Gaussian. Okay, so with this state space model, we are going to write the equations that will take us from kth time instant to t plus 1 time instant. Now this is actually divided into two steps. The first one is called time update. Okay, in time update, actually we make use of the state transition one and go to k plus 1 time instant. So we take the estimate xk hat and its error covariance at time instant k. Use the state transition model to go to k plus 1 time instant. Okay, so we have the time update equation first. And we are actually applying this one. Earlier I gave you an exercise where you had to find the mean of y, mean and covariance of y from the mean and covariance of x, and they were related with a linear equation. The same approach you need to use in this case to go to the next time instant. So you have the mean and covariance of xk at k plus 1, kth time instant, and use the state transition model to go to the k plus 1 time instant. The same thing actually you have to do what you did for that exercise. The same thing has to be done. And we have put negative sign in the superscript. The negative sign means that we have not actually included the measurements. Okay, and positive in the superscript implies that we have included the measurements in our estimate. So here we are just going to the k plus 1 time instant using the state transition mode. Okay, and then the covariance matrix. U is deterministic, so it will not have any contribution to sigma, just like that B vector, which was deterministic, and you found that in the expression of y, covariance of y, we didn't have B. Similarly, UK will not have any contribution, but W is again a noise. W is modeled as noise, so Q will come. Okay. Now since we have not included the measurement at k plus 1 time instant, but got some prediction of the estimate and its covariance at k plus 1 time instant, this prediction is called a priori estimate. This is a priori estimate. A priori. We are just using the state transition model to go from time instant k to time instant k plus 1. Okay. Next we will have measurement updates. Here we incorporate the measurements. Okay, so we will incorporate the measurements here, and this one we call a posteriori. Okay, now how do we update the estimate using the measurement? You will find all the derivation in that material. The a priori equations should be familiar to you because you did that exercise, simple exercise. In the second term, we actually incorporate the measurement. So the first term is actually a priori. We are incorporating the prior information. And the second one considers the measurements. Okay. What is K? K is called Kalman gain. And what is the expression of K? Kalman gain can change with time. So RK plus 1 is the error covariance or measurement noise covariance. And this expression, if you refer to the linear MMSC C matrix. So this is the C matrix. Now you just see P H transpose H P H transpose plus W inverse. W was the measurement error covariance. So the Kalman gain has the same, basically same. I would not say same, similar expression, because P here is the initial error covariance, whereas in the case of the Kalman filter we are having a recursive implementation. So instead of using P, we use the previous, the a priori error covariance sigma K plus 1 minus, and then in place of W it is R, because in this case W is the, in case of linear MMSC we have used W as the measurement noise covariance, but for the Kalman filter we used a different notation R. Otherwise they have actually similar expression. So this is the Kalman gain, and then how about the error covariance? We have updated the estimate. Here we have updated the estimate. We should also update the error covariance. Error covariance also has similar expression as the linear MMSE. But instead of using P, since we used a batch of measurements, we have had P, the initial one. So this was the error covariance we got in case of the batch estimator. Just now we discussed that C has similar expression as K, right? H is the measurement model metric, but the dimensions are different. In case of the batch estimator, we are processing all measurements together, whereas in case of the Kalman filter, we are processing one measurement at a time. Okay, the dimensions are completely different. And here also we have P. P is the initial error covariance, whereas in case of the Kalman filter, we have this a priori error covariance. This is the a priori. But otherwise they have similar expressions. So we know how to go from K time instant to K plus 1 time instant, right? But how can we start this? We need to initialize. Initialize as this one. So assume that you know this. This is for the first time instant. To start with, you need to use this. What is P? This is sigma. So we should provide some initial guess in the form of initial estimate and initial error covariance, and then apply this equation. So from this instant we can do time update, right? We can do this one to get the estimate and error covariance for the first time instant, and then we can do measurement update to do the same, I mean to incorporate the measurements. So this will give us the estimate and the error covariance for the next time instant, and we repeat this process. Okay. Now your task is to implement the Kalman filter equations for that example problem. Now in this case, you have to identify all these different matrices that are required to find the estimates. Okay, and each time instant we just have one measurement. Okay, I gave you a number of measurements, right? Just like the MMSE, where you used one measurement at a time, here also you have to use one measurement at a time. Okay, so implement the Kalman filter for that example and compare the estimate with MMSE and linear MMSE or batch. So yesterday I told you to do this for linear MMSE, and after that you need to do the same for using the Kalman filter. Okay, you need to implement the Kalman filter uh, for that example problem. Find the estimate of x is a constant there, find the estimate of x, and then compare it with MMSE and linear MMSE. So I want to know your conclusion. Is it clear to you what you need to do? Yes or no? Tell me clearly whether you understood or not.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, I'll take, last week I told you that if needed, I will take some extra time, so I think I may not require more than 15 minutes. Within 15 minutes, I will give you another version of the Kalman filter and then we'll stop, okay? Okay. Now see, the state transition model or the state space model that we have considered in the Kalman filter equation is linear, right? If you see the state transition model, we just have the state transition matrix A, and then the measurement model here is also linear. We have this matrix H matrix, right? But generally in navigation, we do not have linear models. Either the state transition model will be nonlinear, and the measurement model can also be nonlinear, or either of them can be nonlinear. Okay, depending on what problem you are considering, what application you are considering, what types of sensors you are considering, you may or may not have linear models. Generally, one of the two will be nonlinear, either the state transition model or the measurement model. But sometimes, depending on sensors, both can be linear. So we need to deal with nonlinear. The original Kalman filter equations were derived for a linear system, linear state space model. Now there are different versions of the Kalman filter that deal with nonlinearity. We are going to briefly talk about the simplest of them. Okay, and also note that in the case of GNSS, we generally use the weighted least squares and Kalman filter. Since the GNSS measurement model is not linear, we have to linearize the measurement, nonlinear measurement model. You already know how to linearize the nonlinear measurement model in the case of WLS, right? Next, we are going to see the simplest nonlinear version of Kalman filter, which we generally use for GNSS. And it's called extended Kalman filter. Okay. This is the simplest of all different nonlinear versions. Okay. So let's assume a nonlinear state space model. Since A is nonlinear, and we'll ignore UK. Let me write small a. Okay, this is not PDF. This is a set of nonlinear functions. We can have UK, but generally we do not have any UK in navigation, so I am not writing UK. Okay, so here we have nonlinear state space model. Other things are the same as before. We have process noise, we have measurement noise, and they are again uncorrelated and they are Gaussian, assumed to be Gaussian. They are assumed to be Gaussian. In the real application, they may not be Gaussian distributed. Then you are making another approximation. Okay, that will introduce an error. But in the traditional implementation of Kalman filter, we assume the noise to be Gaussian distributed. Okay, so with this nonlinear state space model, again we'll start with the estimate and error covariance at k time instant and go to k plus 1 time instant. The same thing we'll do now for a nonlinear state space model. Okay, so I'll give you the time update step. First, so this is how we do the time update. A priori, that's why we have negative sign in the superscript. Now this looks similar to what we wrote earlier. The only difference is this f. What is f? F is actually the Jacobian of small f. So F is actually Jacobian of small f. Now it is not necessary that f is constant. Okay? F can also be a function of time. Similarly, h. It's not necessary that they are constant. They can also be varying. Jacobian, we already know what Jacobian is. We actually take each element of f. F is a set of functions, and then take partial derivative along the row with respect to different states. We assume that capital X, the state vector, has dimension n cross 1. N cross 1, therefore f has to be a set of n functions. And the Jacobian is a matrix of dimension n cross n. Okay? Then for measurement update, we have these equations. This is the same as before. Only difference is in the second term. Here, instead of having a linear equation, now we have a non-linear H. Earlier we multiplied the capital H matrix, right? But now we have a non-linear H, and then the Kalman gain. Now instead of small h, here we cannot have any non-linear term. We have to actually take the Jacobian of small h and multiply that. Rest is the same as before. Since in the model we assume that small h can vary with time. Everywhere in h we should have k plus 1 in the subscript. Okay, so what is capital H? It is the Jacobian of, we already discussed the Jacobian of the nonlinear measurement. And this is M cross N matrix. we have m measurements. The dimension of y is m cross 1 at a given time instant. In that example problem, m is equal to 1 because at a time we have only one y, one measurement. Okay. So the Jacobian is of dimension m cross n because we have m measurements and n states. Right, so m measurements means we have m h small h m functions, right, and then we need to take the derivative of each function with respect to each state. There are n states, so along the row we have n elements, along the column we have m elements. That's why it's a m cross n matrix. Okay. um, uh, the same thing has to be done here also. We need to initialize it with some x naught and sigma naught and then recursively continue as and when we get some measurements. Now there are different ways we can efficiently implement the curve filter. There are different versions of curve filter. What we discuss is most basic, okay, and the simplest of all. I'll conclude the discussion of filtering and estimation by quickly giving you some important Kalman filter properties. Okay, the first one is this: when x naught is the state vector at the beginning, the unknown state vector. This is w, process noise, and v. They are jointly Gaussian. So if you consider the joint PDF of this, and the state space model is linear, KF is the best filter. Kalman filter is the best filter. So if you design some other filters under these circumstances, when x naught, w and v are jointly Gaussian means individual PDF, Marchian PDF are also Gaussian. Okay, they are jointly Gaussian and the state space model is linear. Kalman filter is the best of all filters that you can design. It has an unbiased estimate, so unbiased estimator. This is an unbiased estimator, and it has the minimum error variance. Now we found the error covariance, right? And in the context of linear MMSE, we also discussed how to find the error variance, estimation error variance using from the covariance. It is nothing but the trace of the error covariance matrix. So if you find the trace of the error covariance matrix for all the filters that you can design for this particular case, you will find that the Kalman filter has the minimum error variance. Error means estimation error variance. Minimum estimation error variance. Okay. Now what if the noises are not Gaussian? If noises are not Gaussian, if W and V are not Gaussian, then KF is the best of all linear filters. You can design a nonlinear filter which will give you a better estimate than the KF. Lower covariance or lower error variance, estimation error variance. But the KF is the best of all linear filters. Now, how do we actually define a linear filter? In case of a linear filter, the estimate x hat is linearly related to the measurement. So let's say b y plus this. So capital B and small b are some deterministic terms, okay, and this is the estimate. So the estimate x hat is actually uh, mm, uh, related to related to y this way. So when we have a representation like this, we call this a linear filter. Okay. The third property, which is very important, is it assigns appropriate weights to prior information and measurements. Through the Kalman game. How does this happen? Now this happens through this measurement update equation. So I'm just writing the the linear version. So in case of nonlinear implementation, we should have small h. Okay. Now this is a priori. So this actually represents prior information, whereas this term actually incorporates corrections based on measurements. Now what happens when the state transition model is very accurate? So if the state transition model is accurate, then actually if the state transition model is accurate, this implies Q, the covariance matrix of the process noise, is actually lower than the measurement noise covariance. Okay, by putting this sign, actually I mean the individual elements. If you consider the diagonal elements, you will find that Q has much smaller. Generally, Q is a diagonal matrix. R also we generally consider as diagonal, but it's not necessary that always R has to be diagonal. But in the traditional implementation, the usual Kalman filter implementation, Q and R are diagonal. Okay. If they are not, then we need to incorporate that properly. But Q and R are generally diagonal matrices, and by putting this much greater sign, I mean that the individual diagonal elements, if you consider the magnitudes of the diagonal elements, you will find that Q is much smaller than the corresponding R matrix. So in that case, the filter knows that the state transition model is more accurate and it will give more importance to prior information the first time. Okay. Now, what if the opposite happens? If measurements are more accurate? Then actually the second term dominates. Okay. Now this relative importance to both terms, the prior term and the measurement term, is actually included through this Kalman gain. So in the first case, when Q is much smaller than R, automatically the Kalman gain is small. Okay, automatically you will find that the Kalman gain is small. Therefore, the first term dominates. Whereas for the second case, when the measurements are more accurate, meaning R is smaller, then the Kalman gain becomes large. As a result, the second term dominates. So this way, through the Kalman gain, the filter assigns appropriate weights to both prior information and measurements, which is an inherent property of the MMSE estimator, and the Kalman filter is as a linear MMSE estimator, and it preserves that property. Okay, and I think I missed one more thing in this case. When we are calculating the Jacobian matrix, we need to, so this will be a function of x. So when you find this matrix, you will find that this is a function of x, and we need to linearize this one about x k plus. Okay, so you need to linearize it about this xk plus, and for the measurement model Jacobian here for h, again we need to linearize, and that linearization should happen okay. So when you find the Jacobian matrix, you will see that it's a function of x. So which x will you put? The best that you have at that point is the a priori estimate, because by then you have done the time update and you have the a priori estimate, and that a priori estimate can be used to find the Jacobian of the measurement model. Whereas for the Jacobian of the state transition model, the best thing that you have is this. Okay, so you linearize it about the a posteriori estimate of the previous event. That's it about filtering and estimation. I took more time than what I said, but that's all for today. Tomorrow you have the test. So in the first class you have the test from 11 to 12:15, and after the test we'll discuss the answers. And the syllabus for the test is up to yesterday's class, and I also sent you 2 emails. Don't think that just because attitude and filtering are only included, you do not require some basic concept. For example, coordinate coordinate frames. So we discussed 4 primary coordinate frames. So you may require to use those frames while solving problems. So don't think that those basic concepts of navigation will not be required. WGS84 model, then coordinate frames, they are actually integral part of navigation. So while formulating problems, while solving problems, we cannot think that they will not be required. Okay? Any question? Fine, that's it. You can leave now.
Thank you, ma'am.